Okay, so we talked about what vectors are in a little bit of abstract terms. So I want to kind of bring us back to reality and problems here for a second. So what I'm going to do next is talk through two of the most useful properties of vectors and how we can use those properties to manipulate physical objects like velocities, for example, or momenta later on. Okay, let's hop in. All right. So, part three, vector properties. There are two properties we're going to talk about. We're going to talk about addition and multiplication. So this is just like how to manipulate vectors, how you can do things with vectors. So the first thing I want to mention is multiplication by a scalar. So if I have a scalar, so a scalar is just a number. Say I have a scalar a, that's 3, and let's say I have a vector b with a vector hat with, I'll call b 1 comma 1. Okay? So if I were to multiply a times b, what I do is I can just pull the uh, scalar inside the vector and apply it to each of the components. So this is a times bx, comma, a times by. Okay, so this is this is multiplication by a scalar. This is the property. This is how this works. Okay, so if I do that, what happens to my vector? I go from a b that is 1 unit long, here's b, or not 1 unit long, sorry, it's root 2 units long, because 1 squared plus 1 squared square rooted is root 2, and it just points up and to the right, over 1 unit, up 1 unit on my x, y plane. Now, if I multiply it by a, so a times b, well, that's 3 times as long. That's going to be at the point 3, 3. So this is a times b. So the red one here is my b vector, and if I just scale it by some constant, I'm going to get out a different but same kind of general line it sits on vector. So boom, 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 boom. Okay, so a times b is at 3, 3 in this case. So if I plug in the values, this is 3, comma 3. That's how multiplication by a scalar works. It just, I say, scales the vector. It lengthens it or shortens it. Okay. Another thing that can happen when you multiply a vector by a scalar is it can flip it. So this only happens if the scaling value, the scalar, is a negative number. So for example, like the most common example here, or the easiest, simplest case, is say that I had a vector 2, comma 4. I'll call this vector A. And then I just multiply it by negative 1. So scalar here, negative 1. Well, what I get out, if I just apply my rule from above, what I get out is negative 2, negative 4. Okay, so the vector that used to point, let's draw it on a graph. Here's x and y. 1, 2, 1, 2, 3, 4. 1, 2, 1, 2, 3, 4. So this vector a, 2, 4, and here's negative a. Negative a is negative 2, negative 4. So a points at 2, 4. Negative a points along the same line, but now in the opposite direction. So multiplying a vector by negative 1 preserves the length, but it switches its direction. Okay, the next property I wanted to talk about is vector addition. So there's two ways to think about vector addition. Last time we talked about these two different representations, the component representation, vx, vy, whoa, vx, vy, the component representation, and the graphical representation, from which I know the magnitude and the direction. These are my two pieces of knowledge instead. There are two ways to think about vector addition corresponding to each of these ways of thinking about vectors. So here's the first way that I think of vector addition. If I've got two vectors, a and b, so a plus b, that total vector is going to be ax plus bx, comma, bx, or sorry, ay plus by. There we go. So what we say here is that vectors add component-wise. Vectors add component-wise. So if I were to write out these left two vectors as ax comma bx, or sorry, ax comma ay, oof, typos all over the place, bx comma by, they just add component-wise. So the things that are in the first index, those get added, and the things that are in the second index, those get added in the second index up here. All right, so concrete example, say I had two vectors, I'll make them a equals 1 comma 1, b equals 2 comma 4. All right, so a plus b is going to be 1 plus 2, so that's the first component of a and the first component of b, comma 1 plus 4, the first component, or the second component of a plus the second component of b. So in total, I get the vector 3 comma 5 out. Okay, so that is the component-wise way to look at it. Let's look at the same example using the kind of like more graphical, the more graphical perspective, using graphical ideas. Okay, so if I have two vectors, a and b, let's go ahead and draw them in. I'm going to make b red here, just to make my life a little bit simpler. There we go. Make b red. So if I have a pointing at 1, 1, a pointing at 1, 1, and b pointing at 2, 4, 2, 4, boom, there's b. The sum a plus b is basically the two vectors added head to tail. So what I can do is I can take, let's say I take b and slap it on top of a. So this is one place where a Zeitboard is really useful. So I'm going to move my vector b so that its tail is attached to a's head. So this is what I mean by head to tail addition. If I do that, if I start vector b using using a as its head, then I get out my total vector. So my total vector should be at 3 comma 5. Okay, so I know from before by adding it together, they should be at 3 comma 5. So let's double check. 1, 2, basically 3. My axis isn't great. Pretty much 3, and 1, 2, 3, 4, 5. Perfect. Okay, so we call that head to tail addition of vectors. This is the graphical way to think about it. This is the just kind of pure numbers way to think about it. Both are useful. Notice that these two vectors, when I summed them up, they added up to a vector that was longer. That doesn't have to be the case. That doesn't have to be the case. Cool. Vector subtraction, so if I did b minus a, say, b minus a works kind of the same way, except for that I apply the negative sign to my a. So this is like, basically is the same as the vector addition of b plus negative a. So if we work that one out real quick, what do I get? I get 2 minus 1, comma 4 minus 1. So I get out the vector 1, comma 3. And graphically, I'd represent this by first drawing in b and then adding negative a to it. So it's still just head to tail addition. I've just made a flip around the other direction. The tail of a would be attached to b's head here. Okay, the last thing I wanted to use this video for was to provide a quick refresher on trig using SOHCAHTOA. SOHCAHTOA. So if you're already comfortable with trig, feel free to just skip on to the next video. It's not a huge deal. I just wanted to talk about it for a moment. So trigonometry relies on a triangle. We're talking about a triangle, and it's useful for that triangle to be right. So we're going to say the triangle has a 90-degree angle somewhere in it. So each of these legs, I'm going to call, let's say, x1, x2, and we'll call this one xh, hypotenuse, for the length of this this upper one. So tells me that the sine of theta is the opposite over the hypotenuse, opposite over hypotenuse. So that'd be x2 over xh here, hypotenuse. The hypotenuse is always directly across from the right angle. Cosine of theta is adjacent over hypotenuse. So adjacent is the one that's not the hypotenuse. So that's going to be x1 over xh. All right, and finally, tangent of theta tells me opposite over adjacent. That's going to be x2 over x1. That's SOHCAHTOA. The middle letter is the one that is on the top of the fraction. The final letter is on the bottom of the fraction. And the first letter tells me the function. Okay, I think that about wraps it up for this introduction to some properties of vectors. Next, we'll be talking about momentum.